Right now, floating in space, there's a telescope that was sent up for one job: to confirm we'd figured out the universe correctly, to prove our physics textbooks were right. Instead, it broke everything. It found a star that isn't burning fuel, it's burning dark matter. It found galaxies that aren't galaxies at all. It found a planet that should have lost its entire atmosphere billions of years ago and somehow hasn't. And it watched 5 galaxies slam into each other at a point in cosmic history when that collision shouldn't have been physically possible. This telescope is the James Webb Space Telescope, the most powerful one humanity has ever built. And the 5 things it just discovered are quietly rewriting the rulebook on how stars ignite, how galaxies form, and how planets hold on to their air. Before we get into it, if you're new here, hit subscribe and turn on notifications so you don't miss what's coming next. Now, let's get into it. The rules we thought were unbreakable. For decades, scientists relied on a framework called the Standard Model of Cosmology. It lays out a few basic, dependable rules. Rule 1. Galaxies take billions of years to form. Gravity is slow. Our own Milky Way took roughly 13 billion years to come together. Rule 2. Stars shine because of nuclear fusion. A cloud of hydrogen collapses under its own gravity until it's hot and dense enough for atoms to fuse, and that fusion is the light we see. Rule 3. Black holes grow gradually. As a black hole feeds, the material falling in heats up and radiates light, and that light pushes back, choking off the black hole's own food supply. This is called the Eddington limit, and it means becoming supermassive takes billions of years. Rule 4. Planets inherit their chemistry from their star. A planet and its star form from the same cloud of gas, so they should share the same chemical ingredients. Keep these 4 in mind. James Webb is about to break every single one. Discovery 1. A star that doesn't burn like a star. Webb pointed itself at one of the oldest corners of the universe and found an object called JADES GSZ 140. Its light is only 300 million years younger than the Big Bang itself, essentially baby pictures of the cosmos. According to the standard rules, anything this early should be small, dim, and barely forming. But this object was bright, compact, and calculations suggested it contained the mass of hundreds of millions of suns. That's the problem. There's no known way to gather that much matter that fast. Using Webb's spectrograph, a tool that breaks light apart into a kind of barcode revealing temperature, composition, and activity, researchers spotted something strange. A clean dip in the light at exactly 1,640 angstroms. That's the signature of cold diffuse helium. The leading theory? This isn't a galaxy at all. It might be a dark star, a massive cloud of pure hydrogen and helium with no fusion core. Instead, it's powered by dark matter particles colliding and annihilating at its center, releasing enough energy to keep the whole structure glowing. If confirmed, it means dark matter isn't just sitting quietly as cosmic scaffolding. In the early universe, it may have been actively shaping how the first objects formed, breaking Rule 2 completely. Quick pause. If this is blowing your mind already, smash that like button. It genuinely helps this video reach more space nerds like you. Discovery 2. Galaxies that were secretly black holes. Webb's deep field images revealed hundreds of small glowing red dots scattered across the early universe, nicknamed Little Red Dots. At first, scientists assumed these were ordinary galaxies. But the math didn't add up. To shine that bright, they'd need to weigh as much as the entire Milky Way, except the Milky Way took 14 billion years to get that massive, and these dots existed just 600 million years after the Big Bang. When researchers ran the spectrograph on them, the light didn't look like starlight at all. It showed broad hydrogen emission lines, signs of gas swirling at roughly 2 million miles per hour. Only one thing in the universe has gravity strong enough to spin gas that fast: a supermassive black hole. These weren't galaxies. They were compact, gas-shrouded black holes glowing as they devoured surrounding material now nicknamed black hole stars. And here's where it gets even stranger. In today's universe, black holes and their galaxies grow together in a fixed ratio. The black hole is typically about 1/1000th the mass of its galaxy's stars. But these early black holes were 100 to 1,000 times heavier than that ratio allows. Some weighed nearly as much as their entire galaxy. The black hole won the race before the galaxy even started building itself. That breaks both Rule 1 and Rule 3 at once. Discovery 3: 5 galaxies colliding where they shouldn't exist. Webb then looked at light from roughly 800 million years after the Big Bang and found something labeled the JWST Quintet, 5 separate galaxies crammed into a tiny region actively colliding, their gravity tearing into each other. Using a tool called an integral field unit, which essentially creates a 3D map of every element across the entire scene, scientists found something they didn't expect: a massive shared cloud of gas connecting all 5 galaxies, plus a clear signal of ionized oxygen spread across hundreds of thousands of light-years of empty space between them. Here's why that matters. The Big Bang only produced hydrogen, helium, and trace lithium. Oxygen has to be forged inside massive stars and then blasted into space by supernovae, a process that takes generations of stellar life and death, plus thousands of overlapping supernova explosions to push that oxygen out of a galaxy entirely. Add it all up, forming massive stars, their deaths, a second generation of stars, more deaths, galactic winds strong enough to expel oxygen, and 5 galaxies finding each other across the cosmos to collide, and 800 million years simply isn't enough time. Yet here it all is. Discovery 4: a planet rebuilding its own air. Closer to home, just 280 light-years away, sits TOI 561, a star nearly 10 billion years old, almost twice the age of our Sun. Orbiting it is TOI 561b, a super-Earth that completes a full year in just 10.5 hours. It's tidally locked one side in permanent daylight, the other in permanent night. Webb stared at it for 37 hours across 4 orbits to measure its dayside temperature. If this were a bare rock with no atmosphere, the dayside should sit around 2,700 degrees Celsius. Webb measured roughly 1,760 degrees Celsius, instead still molten, but dramatically cooler than predicted. That gap can only be explained by an atmosphere redistributing heat to the night side. But here's the catch. This planet has been blasted by intense stellar radiation for 10 billion years. Any original atmosphere should have been stripped away long ago through photoevaporation. So where's this air coming from? The dayside is so hot it's an ocean of molten rock, and that magma ocean is continuously releasing gases, replenishing the atmosphere even as the star burns it away. A billion-year-old tug-of-war still ongoing right now. Discovery 5: carbon from an empty cup. Finally, around a young star called C. Chamaelantis, 500 light-years away, Webb examined a newly forming gas giant and the small disk of material swirling around it, the same kind of disk where moons eventually form. Using mid-infrared light to peer through dense dust, scientists checked 2 regions: the star's large outer disk and the planet's small inner disk. The star's disk contained water vapor and rocky elements, but 0 carbon, none. The planet's disk, however, was packed with complex carbon molecules, including benzene, a molecule that requires both abundant carbon and a strong energy source to form. Since planets pull their raw material directly from the star's disk, the chemistry should match. Instead, the source disk has no carbon, yet the planet's disk is overflowing with it. The conclusion? The region around this planet isn't just collecting leftover material, it's an active chemical factory, generating complex organic molecules from scratch far faster than current chemistry says should be possible. What does it all mean? 5 discoveries, 5 different scales, from the edge of the observable universe to our own cosmic backyard. And one thing in common, everywhere Webb looked, the universe turned out faster, more chemically active, and more creative than the textbooks allowed. This isn't the first time our best theories have hit a wall. Newton's physics worked perfectly until Mercury's orbit didn't fit, and that crack led to Einstein's relativity. Einstein's physics worked perfectly until it collided with quantum mechanics inside black holes, and that crack is leading to whatever comes next. Every time our best theory hits a wall, that wall turns out to be a door. So no physics isn't broken, our map was just incomplete, and the next map, whenever it arrives, will be stranger and more beautiful than anything we've drawn before. We built a telescope, sent it 1,000,000 miles from home, and asked the universe to reveal its deepest secret. And the universe answered, "You don't know me yet." If you learned something new today, hit like, share this with someone who loves space, and subscribe with notifications on so you don't miss the next one. See you in the next video.